All right, so let me say a few things before we start. Man, those screens are really bright now, huh? Especially when it's today. There's a few things I did. Obviously, I posted the grades, right? So the grades are posted. I updated your average eventually with all the tests in my office. You can come by, pick them up later on in the week. So the most important thing is your overall average. Because I had someone email me a little while ago, asking what their average was. They thought it was the total average, but it's the overall average is the most important thing to pay attention to on Canvas in regards to your grade. I also posted a homework which is due on Friday, and tomorrow we have a review session. Well, hopefully we have a review session. Last week we almost didn't have one, but hopefully people show up. We have a review session, and the review session will be posted tomorrow. The quiz is due tonight, and after the quiz is due, I'm going to post the quiz solution. And does anyone know when the next test is, by the way? Next Thursday. So that means that we'll be finishing the material for that test soon, maybe today. So this weekend you don't have the homework. You will have a quiz, right? That's based on what we did last week. But yeah, I'll also post the equation sheet sometime this week too, either tomorrow or Thursday, one of those 2 days. So I also flipped a lecture, an example from the end of last lecture regarding magnetic induction, which is on the homework that's due on Friday. So this is all flipped, right? So the explanation is on there on how to do these problems, but I'm going to go through it quickly because it's kind of an important thing. So I'm just going to summarize what you do to find how magnetic induction works. So for this example, like I said, if you want a slow explanation, you can watch the video. This is going to be a much quicker explanation. So in this case here, you have a square wire that has sides L by L. It's put in a magnetic field in the positive Z direction. And the magnetic field is 0.01 Tesla. The thing is wound 5 times. And the thing you're doing here is you're changing the length of the sides. Because you change the length of the sides, that changes the area of the square, which changes the magnetic flux, which produces an EMF. It also produces a current. And the current goes in a specific direction, which is the whole point of this problem. So the idea is you first have to set up sort of an equation to find a magnetic flux. So magnetic flux is the field times the area times the cosine of the angle between the magnetic field and a direction that's perpendicular to the wire. So that's 2 directions for this case here. Direction perpendicular would be positive Z or negative Z. But in general, what you use is the flux, which gives you a positive answer, which the angle that you use so that you get a positive flux in the end for the answer. So if you use negative Z, for instance, instead of positive Z, which is a direction that's perpendicular to the XY plane, the angle between B and negative Z, the field here, is 180, and the cosine of 180 is -1, and you get a negative answer for your magnetic flux. However, if you use the direction that's in the positive Z direction instead, and then they're in the same direction, and the cosine of 0 is just +1. So that's the one you use. Most of the time, it's 0. Almost all the time, it's 0 for the setups that we do. So it's just B times A gives you the magnetic flux. So in general, the magnetic flux is the field times the length squared, because the length, the area of a square is the length squared. So this is a general equation for the magnetic flux. But what's going on here is like I said, the length is changing. Because the length is changing, that changes the flux. So the final flux is B LS squared. The initial flux is B Li squared. That's B times the final area, and then B times the initial area. Then you subtract those 2 things, divide it by the time it takes to change from one length to the other length, and then multiply by the number of turns it's wrapped around. And that gives you the average EMF, which is what we did there, right? So that's sort of like the battery that's produced in this coil, right? It's the thing that drives the current or produces a current. So the next thing is, well, how do you find the current? Well, if you know the resistance of the wire, this wire happens to have a big resistance. It doesn't really matter what the resistance is. But if you know the resistance of the wire, it's basically just Ohm's law. You just divide the EMF you just found by the resistance, and that gives you the current. These are average currents because, well, for more than one reason, but that's what we're calculating, right, is the average EMFs, because we don't do calculus here, and the average current. So the big thing is, what about the direction of the current? Because it either goes counterclockwise or clockwise. There's a definite way it goes. So the idea is if the flux is decreasing, as it is here, so the reason why it's decreasing is because you go from 0.2 meters to 0.1 meters, which means the length is getting smaller, which means the area is getting smaller. If the area is getting smaller, that means the flux is getting smaller. If the flux is decreasing, it means that the current will go in a way to create a field that's in the same direction as the field which created it in the first place. So the field which created it in the first place is in the positive z direction. So the current will have to go in a way which creates a field also in the positive z direction. So to do that, basically you point your thumb upwards, right, in the positive z direction. When you do that, your fingers scroll counterclockwise, and therefore the current would be going counterclockwise around that square, right, when you do this. Then for the second one, it's the same picture, except the length is fixed, right? These are two different ways you can change the flux. Either change the area of the coil or you change the field. So in this case here, the length is fixed, but you're changing the field, right? So the field's going to change, the amount of the field. It's the same idea. You find the general equation for the flux. It's B times the area, B times L squared, but this time the field's changing. So the final flux is BF, the final field times L squared, the initial flux is BI times L squared. But nonetheless, you subtract those two things, put them in the absolute value, divide by the time it takes to change from one field to the other field, multiply it by the number of turns, and that gives you your induced EMF for this case here. Once again, if you want to find the current, you just divide that by the resistance of the coil. In this case, it was 2 ohms. So you divide that by 2, and that gives you the current. But once again, the current will either go clockwise or counterclockwise. So the idea for this case is, see, the field goes from 0.2 to 0.4 Tesla. So that means it's getting bigger, right? If the field's getting bigger, it means the flux is getting bigger. So if the flux is getting bigger, the current will travel in a way such that it produces a field opposite of the field which created it in the first place. So the field that created it in the first place is in the positive z direction. So the current has to go in a way to create a field that's in the negative z direction. So if you point your thumb down in the negative z direction, your fingers scroll clockwise. So if you increase the field, the current will go clockwise to produce a field in the negative z direction, which is opposite of the field which created it, right? And that's basically how it works for magnetic induction for these two cases, right? Either changing the area or changing the field. All right. Does everyone understand that? All right. So I guess that's already fun. And this is where we're going to end. It's kind of a weird video because I'm going to stop it right now because this goes in test 3 and then after this goes in test 4. So this is exactly where test 3 ends. So test 3 starts, I believe, with RC circuits, right? So it's charging, discharging RC circuits, magnetic force on point charges, motion of point charges in magnetic fields, magnetic force on wires, magnetic moment, circular field by circular wires, field by solenoid, field by straight wires, infinite straight wires, force per unit length, and this, magnetic induction, for these two cases where you're changing the field or changing the area, right? That's where it ends for test 3. I might have forgot something minor, but that's the gist of, just about everything, right? I mean, it's everything from test 2 until now, right? Starting with RC circuits. Okay, so let me stop the video because this is going to go in test